Hello again. We continue our lecture series on SMT-streamlined software model checking. We are going to do part 2 on function summarization-based model checking. Here's the schematic representation of the ideal application of model checking. We have a program to check. We have its source code and some properties which we want to see if they are satisfied or not. And we have a tool available for us. And ideally, we would like to apply it to the program verification in a fully automated manner, in a push-button technology way, such that the tool does its job and tells us if the property is satisfied or not. However, this is not the ideal world, and realistically speaking, whenever we have a program to check, we have different situations. We have a tool and we have a particular instantiations, some particular inputs or library stubs which are available for the program realization, and some properties to check. Based on this particular environment, we are analyzing the program and we see if the given properties are satisfied or not. Then some inputs could change and we have another case to check. And the model checker run again against the same code, against different properties, different inputs. But what's interesting to observe is that most likely the model checker will repeat the job it's already done in case 1. And we have to do it perhaps many times. And every time we're performing the verification task, seemingly we are redoing a lot of steps which the previous verifications have already done. Our intuition here is that perhaps it could be avoided, repeating the tasks of analyzing the system again and again. We really observe the need for incremental analysis. So when we have the same code, but different environments for this code, execution, and different properties to check, perhaps we could, in the very first run, to remember some information, to remember some computational history, and use it for the consecutive verification runs. Furthermore, we could have a scenario when we have a system which changes. It could be just an update due to the customer request, it could be a bug fix, but it's just the evolution of the system. What are we going to do? Seems like we have to restart from scratch to re-verify the system again against the same properties we already checked on the original version of the code. Perhaps this also could be somehow simplified by using incremental analysis. And our solutions for both of these cases, when we verify the same code or different due to evolution of the system, would be to use some symbolic abstraction which we would compute fully automatically. And this abstraction would help us to remember what we already done. We learned about the system while verifying it in the first run. And then for every consecutive run, we would reuse it instead of the exact full recording of the system. Ultimately, our idea is to come up with a procedure which will be much more efficient. And it's exactly what our tools are implementing. To understand it, let me explain to you how exactly it's done. Function summarization is a technique which creates and uses of approximations of a function behavior. It contains information which is only relevant to prove properties. All other information is simply dropped. And it's expressed using functions input and output parameters. And it is used, as I already mentioned, in both scenarios, when we verify the same code but different properties, or we verify different systems but against the same properties. These two scenarios are the tools which we are going to see in this lecture series, HiFrog and UpProver. Let's illustrate this concept of summarization. Here's some sample code. There is a function main which calls function f inside of its body, and there are two properties to verify. The properties are highlighted in red. And supposedly this is very expensive. Supposedly it takes a lot of resources to verify even a single property. Do we have to repeat the task and use the same amount of resources for the next property? Perhaps we could learn something such that we can, when we refine the second property, it could be useful for us to simplify the task of analysis. You already see on the slide actually proposed formula, which could be over approximation of the real behavior of function f. As you can see, this proposed formula does not refer to particular values of variable a, for example, as it's happening in the actual implementation of function f. It simply observes that whenever a is positive, function returns a positive value. And it could be clearly seen that this information is sufficient for verification of both properties. So there is no need actually to trace down the actual computations going in function f, while we can simply use this knowledge and substitute the function, the actual function, with its summary and use it for the verification of the properties. Now, how do we compute this summary? Ultimately, it should be a fully automated procedure and easy to extract from the program code. We are going to use what is called Craig interpolation. It's a popular concept these days, used in various disciplines, in particular in program verification. It's a symbolic technique which deals with symbolic formulas, and we are going to use it. Because we are doing a logic-based verification, it's really nicely suitable for the integration with SMT or SAT-based solving. First, let's understand this technology and then see how it could be employed for the tasks of functional summarization. Craig interpolation is defined as follows. Given mutually unsatisfiable formulas A and B, an interpolant is another formula I, such that it satisfies the following three conditions. A implies I and B is unsatisfiable, and I is defined over common symbols of both A and B. The illustration on the slide demonstrates two formulas, A and B, which are unsatisfiable. They don't share any space, as it's clearly seen. I is another formula, such that it over-approximates A, meaning that A implies I, but it's still unsatisfiable with B. As you can see, the green area never overlaps with gray. And this formula I is also quite clearly can be seen is not unique. You might have various candidates for the interpolation, such as here it would be I prime or I double prime. And this is a very nice observation, which will be very handy for us as well when we apply it for program verification, because we might have sometimes stronger interpolants or weaker interpolants for various verification tasks. We will get back to it later in the course. Now, how it's all going to be used for function summarization in our tools in SMT-based model check. We are going, as I already told you in part 1, we are doing bounded model checking. We will be constructing a BMC formula by means of some pre-processing. First, we will be going to do SSA form encoding, and then it's going to be translated into corresponding logical encoding, as we already seen illustrated before. But now, in addition to logical encoding, we are going to introduce additional constraint. We are going to do special partitioned encoding to put focus on the functions. Our formula, bounded model checking formula, will clearly be partitioned into segments, partitions, which represent all the functions used in the program. And since it's bounded model checking, of course, we are going to do loops and recursive function calls unwound up to a given bound. Then this formula is going to be given to a corresponding solver, which is going to take the logical encoding we produce together with the negation of the property to be verified. And if the solver returns unsat, we know that system is safe. The possible error state is not reachable. If it returns sat, it's the other way around. It means the error state is reachable, and we know that the solver finds an error for us. We are applying crack interpolation after SMT solver returns unsat. We really need a bootstrapping step when a program is verified against some property and this property is found to be safe. If it's the case, such solver returns as unsatisfiable core, and we are going to use it to help us to construct summaries. Summaries are going to be then stored and reused for all consecutive runs. How are we going to construct the PBMC formula, partitioned bounded model checking formula? Here is an illustration. Here's some control flow graph of some program, and as you can see, is the root function, main function, which possibly could call up to six other functions in a way represented in the picture. And each function has its own body of all the computations which it performs. For the sake of simplicity, we don't illustrate it here. We only focus on the functions. And so what's going to happen, we are going to remember this information about how functions are being called, who is the callee, each function, and construct a formula as a conjunctions of these partitions. Each partition represents exactly the body of a particular function. We put it together in conjunction with the negation of the property which we are checking, and because the negation of the property represents a potential error, and we give this formula to the solver. If solver returns unsat, we know the property is satisfied, so error state is not reachable. And now it's a good information for us to know that system is safe, and we are going to use this safe information to help us to construct the interpolants. How are we going to generate the summaries? Looking at the same example again, we are going to do iteratively for each function. So for example, for function F1, we are going to decide, we're going to choose this fragment in the formula as fraction A, and the rest of the formula is going to be part B. So this is a formula which will help us to employ the crack interpolation computation. So there is A part, there is B part. It means we can always compute an interpolant I such that it satisfies all the properties of the crack interpolant. For function F1, we can easily extract interpolant I1. And we will do it iteratively for all function calls. Based on this procedure, we will have a collection of different interpolants for each function which is present in the system. Each of these interpolants is over-approximation of the actual function, and this over-approximation is perfectly suitable for us to use instead of the actual function encoding. So, for example, here's an illustration of the properties of our interpolant-based summaries. First of all, we know that each fraction A implies the interpolant, and for example, if we look at this fraction together, so we can see that our interpolant I5 is the composition of several interpolants, because it preserves the parent and the child relationship in the control flow graph. So, and the rest of the formula, the B part, which you're using to compute the interpolants, remains unsat. And clearly that for each interpolants which represent the composition of the interpolants, they're all defined over shared symbols. There's the shared variables which all the functions using. So now, how are we going to do verification with these summaries? We are going to use them instead of the actual system representation. And when we are using them, if no error is found, if the model checker reports that system is safe, we know, yes, it's indeed safe, because all of our summaries are over approximations. They don't miss any actual behaviors of the system. This is fantastic, it's very useful. Now, we could also have a situation when together with the summaries, an error is detected. So now it could be two cases. The error could be not real, it could be spurious. And this spurious result could be due to the fact that we are using over approximations of the summaries. And we will have to deal with this somehow to really figure out if we really found the spurious error or not. Well, if it's not a spurious error, then we will clearly know that it's a real bug detected. So how are we going to do it? Our procedure is going to do it by means of refinements. The refinement procedure is going to identify problematic summaries, the summaries which are involved in the path which leads to the error, and we will substitute these summaries with more precise representations of the actual code itself if we want to continue our verification runs. Here's some high-level illustration of this concept during the program execution. Some parts are represented by the summaries which we are using to replace the exact code. And we will, supposedly, this execution brings us to the bad state, to the error state, and to the violation of the system. We will, by error trace analysis, which a solver generates, we can identify which exact summaries are the problematic ones, potentially problematic ones. By doing the dependency analysis between the error, between the property and each of the individual summaries, we can figure out if it's indeed the case that a particular summary causes spurious behavior or not. And once we identify the summaries, we are going to simply substitute them with precise representations, for example, to eliminate spurious behaviors. Here is the brief illustration of what I've just explained. So we have a program, which is the collection of function calls, for which we create a symbolic formula. And each fraction of the formula represents a function encoding. And supposedly, for the verification of new properties of the same system, we decide to use some summaries which we already have in our database. The red boxes represent these function summaries we decide to verify. We have a partially precisely encoded system and a partially abstractly represented system. Altogether, while verifying the properties of the system for each consecutive run, we always give this formula to the solver, which is checking if the formula is satisfiable or not while verifying new properties. If the solver returns SAT for the formula we provided together with the summaries, we know that there are two possible outcomes from this. It's either a real error was found or this is a spurious failure. We'll need to try to understand, is it real or it's spurious? And it's going to be done by means of analyzing the SAT assignment which a solver returns. So the SAT assignment represents an error trace which leads to the bug. And this error trace will be analyzed, and the possible function summaries which were involved in this error trace will be examined. Each function summary which is present in the error trace will be checked using data dependency analysis to see if there is a dependency between variables used in the function summary and the property. If there is such dependency, then we know that it's the summary causes the failure. If there is no such a dependency, it means function summary is not responsible for the error which was detected by the solver. Therefore, the error is real. This is the underlying concept of how HiFrog operates in the presence of function summaries. This function summarization-based approach is the core of our HiFrog and UpProver tools. Here is some references, by the way, to both tools which you can find and experiment with and use for your research. Both tools are using as a pre-processing step SMT-prover framework. It's a framework for symbolic encoding and verification of programs written in the C programming language. We are using it as the initial step before we start implementing function summarization on top of it. And our framework uses, since it's SMT-based approach, so both for BMC checks and for the computation of function summaries is using SMT solver, our SMT solver OpenSMT, which is also available at the following website for your experimentation. Altogether, here's the architecture of HiFrog technology. We already covered pretty much all of these steps, and let me walk you through it again to make sure it all gets together in a complete picture appropriately. We start with a given program and some assertions, some claims, it's all synonymous, some properties to check. And we start pre-processing our description, trying to convert it into a symbolic formula. Our SMT encoder, as I already told you, allows us to encode it into Boolean representation or into SMT representation, such as linear arithmetic, uninterpreted functions, or bit vectors. Given this, we might have options how exactly we want to encode, so the tool operates such that you can always specify which logic you want to use for creation of the symbolic encoding of your system. Once it's been encoded, it's being given to a solver, SMT solver, which is going to, together with the property encoding, see if the formula is satisfiable or not. So here, actually inside of this box, which represents the solver, you see a lot of internal steps, which we have not talked about yet. This will be covered later in our lectures. So for now, we just treat it as an SMT solver. What's important for you to see is that there are some procedures which we call ITP. This is the decision procedures for the computation of interpolants. So we can compute interpolants for the Boolean logic encoding or for interpreted function or linear arithmetic. It really depends on what kind of encoding you are giving to the solver. For the corresponding encoding, it will use the corresponding interpolation decision procedure. The system starts from bootstrapping. It verifies the system against the given property, and if the property is satisfied, then we are going to generate a bunch of summaries for all functions which are present in the system, and they're going to be stored in our storage of function summaries. And in addition, you actually can see that not only we can automatically compute summaries, but we can also define some user-defined summaries. I will talk about it a little bit later. Now the summaries are available and they can be used to create new logical encodings whenever we are verifying new properties of the system. For each new property, the logical encoding of the system would be consisting of partially precise encoding and partially bindings of summaries, which can be retrieved from the storage. And in case if the solver which does the computation for us returns that the system is SAT, so for these cases we will have to check if it's a real error or not. And if needed, it's going to refine the formula to remove spurious behaviors. This is the summary. It's in a fully automated flow. Every single step is done automatically by the tool. The user does not have to do anything at all. So the system ends up by returning safe if the solver returns unsat, or it's going to report unsafe, and it will internally see if it's a real failure or not. For those cases when it's not real, it's going to do the refinement and move on until it sees if the system is safe or not safe. As I said, in addition to automatically generated summaries, we can also have user-provided summaries. And here an example which illustrates the need of this user interface. Here's an example which uses nonlinear operations. In particular, it's doing sine square plus cosine square operation. Some computations are inherently complex. And sometimes giving the task to a solver to deal with this computational operation could be quite a challenge for the solver to do it appropriately. And but we can observe that this is a very well-known trigonometric function, and we actually know that for the sake of the computation where it's used, it's actually equal to 1. So we don't really have to do the computation. We could potentially just use the information that it should be equal to 1. This would be the summary of this function, which extracting automatically is expensive. But if you just plug it in, then it's very simple. The life of the checker who is doing the verification would be considerably simplified. So our tool actually is doing the following. Since an SMT checker uses a particular format, which is called SMT-to-lib format for encoding of formulas, our tool generates templates for all functions which are used in the system. And if needed, these templates could be instantiated manually by a user from outside based on his knowledge what the function value actually is. And this is quite ugly looking. This template which I'm showing on the screen, I'm very well aware of this, but this is the SMT-to-lib format. So it's actually not exactly meant for the human to read, but at the same time, if you closely look at this, you realize that it's actually quite straightforward to see what would be the return value of the functions. So we can take this template and actually explicitly say that the function should be returning 1 instead of trying to be computed based on the actual operations used in the function definition. So this is one of the features of HiFrog, and we can provide any summary for pretty much any function. The user knowledge could be quite handily exploited. And now it's time for the demo of these two features. I want to show you how function summarization actually works in HiFrog and how user-defined summaries can be used. We'll start with an example illustrating the creation and use of function summaries. First, we are going to look at some example. And we will see that, again, it's just for the illustration purposes, quite a simple computational task. But for the same, to verify the property, if it's going to be safe, if the property holds, it's going to be also, this run is going to be used for the construction of the summaries. And for the next verification effort, when we verify a different property for the same program, we are going to use the summaries which have been computed in the first run. So let's start and see how it's done. First of all, if there are any summaries, we have to remove them to clean the picture. And now we are going to run HiFrog using, for example, array encoding of this program and verify claim number 1. And as you can see, it's quite actually quickly terminated by saying the property calls, it's successful, and it's created some summaries. For the next iteration, we are going to use the same example, but verify a different claim. And to see if it's going to be handy, it's going to help us maybe to be more successful. And actually the tool terminates even faster, as you can see. And it actually reports a considerably small amount of time it was required to see if this new property was also successful. This is the basic illustration. In this demo, you see 2 examples. But if you have large systems, the speed up which you get from the use of summaries is actually quite substantial. And the next example is of the user-provided summaries feature of HiFrog. I already showed you example. There's a trigonometric function, and let's do it here as well. And we will try to avoid the complex computations which would be required in order to analyze the system. We are going to try to provide the information that this function actually return 1. And we'll do it by means of the user input to the system. So we will ask HiFrog to construct a template for us. This is the feature which does it. So the template is being generated, and now it's going to be illustrated. So here we are visualizing the template, and the template already has been added with the information that the return value of this function should be equal to 1. Now, whenever I want to verify this example, and for example, I'm using the LRA encoding of this example, I'm going to require the solver to use the user-defined function, and then the verification actually is spectacularly fast. So if you would not provide this user-defined function, verification would be obvious and I would like to share with you some experimentation which we did with HiFrog against some state-of-the-art software model checkers such as CBMC setups and CPU checker. Our tool HiFrog is using function summarization-based approach for verification of the system, while setups and CPU checker, for example, are counter-example guided refinement and collection approach, and they are not implementing the same procedures, but still, so we can get a very good picture to see who is doing better, who is doing worse. So the STIGA approach, the counter-example guided abstraction refinement approaches, are known to be performing quite well. So we can see how HiFrog compares against them. Furthermore, CBMC is also a very well-known tool to be able to verify complex systems. And we would like to show you some information about our experimentation, comparing HiFrog against these wonderful tools. So our experimentation setup was that multiple assertions were checked separately. So for each of the verification property, we run different runs. And so all assertions hold, so it means that summarization is possible. Here's some statistics with respect to our experimentation. We ran it against a large number of benchmarks, all taken from realistic systems, from a collection of the systems used for the comparison of various verification tools. Some of them come from industry, such as, for example, Microsoft device drivers. Let's look at just one example. For example, the one highlighted in green. It compares how much time in total it took for each tool to verify the system. And the size of the system is indicated by the number of lines of code, the number of instructions present in the system, number of function calls which were present, and the number of property assertions which have been verified. For example, for this 42 example, HiFrog outperforms all other tools. In particular, it very nicely outperforms setups and CPU checker. What is also interesting is to see that HiFrog, together with CBMC, succeed in all examples, while setups and CPU checker, for many examples, either run out of time or memory, or are not able to support the features of the program, so they are not able to produce the result at all. This is quite illustrative, and our observation of all the results we have is that on large examples, HiFrog always outperforms all tools. And if it's a small example, if it doesn't consist a lot of lines of code, something not so expensive, then CBMC, for example, trivially solves it, while since we require the computation of the summaries and we do have to pay the price for the overhead of this computation, HiFrog actually is not as performant as the baseline model checker. However, once again, our aim here is to verify a large system, realistic systems, to put our SMT-based model checker as a routine checker, which is used for the continuous verification of large systems. So, and it really performs very nicely on large examples, is really encouraging. But overall, despite of the added overhead of the procedures which HiFrog has, such as computation of function summaries, such as refinement in analysis of traces, counter-example traces produced by the solver. Despite of all of this, the performance of the tool is quite comparable with the state-of-the-art tools, which don't do any of these tasks. This concludes my presentation of the function summarization-based model checking, and in the next part we will continue with other features of HiFrog.